Hello everybody, welcome back guys. So we are moving on to section 5.3. We've been talking about perpendicular bisectors and perpendicular bisectors in regards to their relationships within a triangle. And now we're going to be focusing on angle bisectors. And in this video we're not going to do anything with triangles, and that will be for the next video, but we're going to talk about angle bisectors, and you're going to use angle bisectors to solve some problems. And there's a couple things I need to talk to you about before we get to those problems. And one of those things is, how do you measure the distance between a point and a line? And so to illustrate that, I've got a picture of a point and a line. Hey, and let's just say that that's point O. Why not? And I want us to find the distance between point O and this line that we'll just call line L right there. Now, there's the reason that we're talking about how you measure the distance between a point and a line is because there are many different ways to get from this point to this line. For instance, I could draw this segment which goes from point O to the line. I could draw this segment here. I could draw this segment way over here. Okay? Lots of ways for me to get from the point to the line. However, none of those that I've drawn so far would be considered the distance or how far that point O is from line L. Because what we're interested in is what is the shortest distance between point O and the line. And if I want to go the shortest distance, what I have to do is I have to measure perpendicularly to the line that O is, well, that we're measuring its distance from. So that orange segment that I drew right there, that is what you would consider to be the distance from O to line L. Always the distance between a point and a line can be measured with a segment that connects the two and is perpendicular to the line. Very important that whatever you're trying to measure from a point to a line, that you always look for that right angle to make sure that it's actually the distance from the point to the line. Okay, now, angle bisector theorem is what we're going to talk about right now. We've already used the idea of angle bisector quite a lot back in chapters 1 and 2. And even later on, we used angle bisector. So you know by now the definition of an angle bisector is some kind of ray or line or segment that divides an angle into two congruent angles. And so let's suppose that in this picture that that's what this ray BP does. Tell you what, I'm going to redraw that ray real quick. It's not quite where I want it to be. There, I like that a little better. Now, so ray BP is the angle bisector of angle ABC, which means that angle ABP is congruent to angle CBP. That you know. What I need to teach you now is something that's true about a point that lies on the bisector of an angle. So something very similar to what we talked about as far as when a point is on a perpendicular bisector of a segment, which I'll draw for you really quickly. We said if a point, such as this one right here, is on the perpendicular bisector of a segment, that it's equidistant from the two endpoints of the segment. So these two distances would be equal to one another, right? I'm about to throw out that word equidistant to you once more with angle bisectors. However, we're not going to say that a point that's on an angle bisector is equidistant from the endpoints of the angle, because there's no such thing as the endpoints of an angle, all right? But what I am going to tell you is that if a point, such as point P, is on the bisector of an angle, then that point is equidistant from the sides of the angle. So the distance from P to ray BA, one of the sides of the angle, and the distance from point P to ray BC, the other side of the angle, have to be equal. Now this is why I showed you how you measure the distance from a point to a line a moment ago, is because now we're going to show you the distance from a point to a ray, which is done the same way. If I want to measure the distance from point P to ray BC, I have to draw a line that's perpendicular to ray BC. Like so. And similarly then, I need to draw a ray that's, or a line segment that's perpendicular to ray P or BA if I want to show how far it is from that point P. There we go. And those two distances have to be equal to one another. Let me write this out. If ray BP bisects angle ABC, then the following is true. The distance from point P to ray BA equals the distance from point P to ray BC. Any point on an angle bisector is equidistant from the sides of the angle. That's the point I need you to take away from this. All right, so let's use that in a couple different ways. I want you to find the indicated measure, and there's two different measures that we're going to be finding here. Now, first thing I'm asking you to do is to find the measure of angle PQR. And notice in the diagram, I've indicated that these two angles are congruent to one another. Now, I need to finish writing an expression for one of these angle measures. Let me do that real quick. Done. In order to find the measure of angle PQR, turns out we're going to need to find the value of x. And I've given you an expression for each of the two angles that were half of angle PQR. Well, they are half because this is an angle bisector, ray QZ. And so we're going to set these two angle measures equal to one another. All right, in other words, the measure of angle PQZ equal to the measure of angle RQZ, which is going to then tell us here that 4x minus 11 is equal to 2x plus 3. And then subtract 2x from both sides, add 11 to both sides, you get 2x equals 14, x is equal to 7. My directions did not tell you to find the value of x, although that was necessary. We wanted us to find the measure of angle PQR. And angle PQR, we could say that its measure is either twice the measure of angle PQZ or twice the measure of angle RQZ, or the sum of the two. I'm just going to write down that it's twice the measure of angle PQZ, which means that it's twice 4 times 7 minus 11. And that's 28 minus 11, that's 17 right there. And 17 times 2 is 34. It's 34 degrees. Okay, there you go. So that's just using the fact that this is an angle bisector, as was indicated again in the diagram. Now, let's go ahead and take a look at how you would find the distance from Z to R. And this one's not too complicated whatsoever because, well, point Z is on the angle bisector of angle PQR, meaning that it's equidistant from the sides of the angle. And can you see how these two segments ZP and ZR represent the distances from point Z to ray QP and QR respectively? And so then since Z is supposed to be equidistant, those two segments have to be congruent. Since then segment PZ is equal to RZ, that's going to tell us that ZR is 3.2. All right, very simple, right? Now there's also the converse of the angle bisector theorem that you're going to have to be able to work with, and this is how that goes. The idea is that I'm trying to determine, is a certain ray actually bisecting an angle without measuring the angles, because that would be, well, you know, in some cases that's the easiest way to go. But let's pretend you couldn't do that. And I wanted to know, does ray BR bisect angle ABC? Well, I can figure that out if I can determine whether point R is equidistant from the two sides of the angles. If it is, then R is on the angle bisector. And if the distance from R to this side does not match the distance from R to this side, then it would not be on the angle bisector. All right, now we're just going to pretend that it does in this case. Let's just go ahead and draw these two things. That would represent the distance from R to ray BA. And this will represent the distance from R to ray BC. And we're going to say that those two things are equal to one another. All right, if and I want to write this for a general statement, not for this picture specifically. If a point is equidistant from the sides of an angle, then it lies on the bisector of the angle. Now, with this converse of the angle bisector theorem, you can have some tricky little pictures thrown at you, and I've got a few of those here, or a few of the different pictures that you might see. All we're going to try to do is for these next three pictures, you see this one, and this one. We'll come back to those latter two later. We're trying to determine, does the ray QM bisect angle PQR? And simply the way we're going to determine that for each of these problems is we're going to see, is this point M equidistant from the two sides of the angle? All right, well, what do you think for this picture right here? Segment MP is indeed congruent to segment MR. Yet the answer to this question is no, at least as far as we're aware, it's no. And I'll write an explanation. Why do you think that this is not the angle bisector? Well, remember that whenever you measure the distance from a point to a line, it has to be perpendicular. If we had drawn these segments that are in green, and they're perpendicular to the sides of the angle, and if we had said they were congruent, that would have been enough for us to say that M is on the bisector of the angle. But without that information, we can't tell that M is equidistant from the sides of the angle. We just know that it's equidistant from one random point on the side of this angle and one random point on the side of this angle. All right, so no, M is not equidistant from ray QP and ray QR. All right, well, let's take a look at the next picture. Same question, can you conclude that ray QM is the bisector of angle PQR? And it's starting to look a little bit more like we can here, because you do see that these two distances, or these two segments, MX and MY, are both perpendicular to the sides of the angle, respectively. However, the answer is still no. And I wonder if you can spot the reason why. All right, what we would have needed in order to state that those two things were congruent was to know that those two distances from M to the two sides of the angle were actually congruent to one another. That wasn't stated to you, was it? All right, well, so again, we're going to have to say no, because M is not equidistant from ray QP and ray QR. It might be, but we don't know that it is, and so we're going to state that it's not. Okay, now one more example here, and this is exactly the thing that we're looking for if we're trying to determine that a point lies on the bisector of an angle. You see, these two segments represent how far point M is from the respective sides of the angle, and those two distances are marked as congruent. So yes, because M is equidistant from the sides of the angle, is your response to this. That's angle bisectors and their very simple property. Thanks for watching, guys. I will see you in the next video when we talk about angle bisectors of triangles. Thanks again. Later.